Hi, everyone. We're getting started with the next set of spotlight talks. The next speaker will be Jungil Ham, and he'll be presenting on drift-free visual compass leveraging digital twins for cluttered environment. Thanks.
Hi, good morning. Hi, everyone. I'm Jungil Ham from Gwangju Institute of Science and Technology. I worked as an international intern at NASA Ames from last year to March this year. Today, I'd like to introduce our novel drift-free visual compass that leverages digital twins for cluttered environments like the ISS. Our method enables drift-free 3 degree of freedom camera rotation estimation for space robots. Recent efforts have focused on developing free-flying robots for space stations. NASA's Astrobi is the most advanced free-flying robot on the ISS, designed for fully autonomous inspection, logistics, and modular payload operations. Also, Interpol 2 by JAXA enables autonomous flight, docking, and recharging, and its last demonstration was recently presented at ICRA 2025. Unlike robots on Earth, space robots can rotate freely in every direction, a full 360 degrees with no resistance. This might sound cool, but it actually causes major challenge for vision-based navigation. Sorry. And it is well known that rotational error or drift is the major source of positional inaccuracy in visual navigation. These videos have to, oops. Okay. The video should have illustrated the impact of rotational drift. On the left, we show a traditional method that estimates both rotation and translation jointly. On the right, the translation is estimated with ground truth rotation. So accurate rotation enables significantly more precise camera trajectory and 3D reconstruction. To this end, structure models have been widely adopted in computer vision and robotics to estimate accurate drift-free camera rotation. The Manhattan world assumption represents structured environment with 3 dominant orthogonal directions. By detecting and tracking these directions, known as the Manhattan frame, we can robustly recover camera's absolute orientation for rotational drift. Because the 3 dominant directions provide a consistent reference, acting like a compass for the camera's rotation. The ISS is an ideal environment where the Manhattan world assumption holds. We designed a 3D visual compass that enables drift-free rotation estimation by leveraging this Manhattan world structure. This is implemented using geometric primitives such as lines and planes, which offers richer geometric context than, say, point features. However, the ISS is an extremely cluttered and dynamic environment. There are numerous wires, laptops, and bags that introduce significant visual noise. This object often leads to excessive outliers, making traditional methods unreliable or even fail entirely. Therefore, robust outlier rejection method is essential for such settings. To address this issue, we use the digital twin of the ISS. Unlike the messy and cluttered ISS environment, the digital twin is free from distractions and contains only dominant static structures. This clutter-free environment enables robust line detection and tracking. We identify meaningful structural lines and effectively discard clutter-induced outliers by matching the line features detected in the real ISS image and those rendered from the digital twin. We name our method DTOR, digital twin-based outlier rejection. Our method robustly extracts reliable structures in cluttered environments. For the line matching between the ISS image and its rendered digital twin, we use glue stick, descriptor-free geometric matching method. For rendering the digital twin at the case frame, we use the estimated pose from the K-1's frame and glue stick line matching. Even when line appears slightly shifted, this does not degrade the matching quality. We detect dominant plane from the 3D point cloud of the depth image using the RANSAC plane detection algorithm, which finds the plane supported by the maximum number of inlier points. When the density around the currently tracked normal vector becomes too low, the system reinitializes a new dominant plane. This allows reliable plane tracking even under structure changes or occlusions. This slide shows our full pipeline for estimating drift-free camera rotation using structural lines and planes. We estimate camera rotation by combining a dominant plane and a single line, which corresponds to the theoretical minimal sampling for rotation estimation. The plane from point cloud gives the first axis of the Manhattan frame, and the line, if it lies on the plane, defines the second, and their cross product gives the third axis of Manhattan frame, enabling full 3 degrees of freedom rotation tracking. This is done robustly using RANSAC after rejecting outliers by our detour method. We conducted our experiments using the SRW dataset, which we established in our lab and published in IEEE Robotics and Automation Letters. This dataset provides real-world ISS sequences with synchronized RGBD images and precise ground truth pose for benchmarking visual navigation in microgravity. The qualitative research shows the accuracy of our method in the real ISS environment. The first column shows all LSD detected lines, including dynamic and cluttered outliers. The second shows structural lines from the digital twin. The third visualizes the matched line after outlier rejection. And the fourth clusters consistent lines by the estimated vanishing directions. In the last column, thick and thin colored lines illustrate our estimated camera orientation and Manhattan directions, while the black lines show the truth camera orientation. So you can see how close the estimation is. We also represent quantitative research on the SRW dataset. Most competing methods struggle in cluttered environments, especially in sequences with large rotation, due to drift or failed initialization. In contrast, our approach maintains low error across all sequences. As a result, we achieve the most robust and accurate rotation estimation, even in highly cluttered and dynamic ISS scenes. In the future, we aim to extend our method toward full 6 degrees of freedom SLAM by integrating it into the 3D Gaussian splitting SLAM framework. As shown here, we align the normal vector of 3D Gaussians shown in magenta with the dominant axis of the Manhattan frame. This regularization improves structure consistency and leads to more stable reconstructions. Our goal is to overcome a key limitation of conventional Gaussian splitting SLAM, which is unreliable normal estimation that causes noisy and fragmented map in cluttered scenes. We plan to apply this approach to real-world ISS data using the clean and accurate Manhattan frames detected from the digital twin to guide numeral alignment. In conclusion, free 360 degrees rotation and cluttered environments like the ISS make visual navigation extremely challenging. And our method removes clutters and enables accurate drift-free rotation estimation in space. Also, this is the first time that digital twin has been used for feature filtering or line filtering, making our method a novel approach. I made a poster, but didn't get to put it. So if you have any question, I'm happy to answer and chat about our work. Thank you for your time.
So you made a digital twin of ISS. Did you have you considered what your data would look like if you were to also add in the mock-ups, like the physical mock-ups that are made for astronaut training? Obviously, you can't easily get to ISS to do scans or anything else, but the one on the ground is much more accessible. I guess given the opportunity, would it help your project if you were able to access?
I'm sorry, access what?
The physical mock-up of ISS that's I believe in Houston and there's one in Russia.
Even if we can access those real, you mean the real actual ISS, right?
So on the ground on Earth, there is a full scale.
So it's clutter free. Like there is no, there's only structure of ISS.
Same type of clutter that they would have in space.
But
I've only been to one of them, but
yeah, it would help if it's strictly accurate design of the real ISS.
I mean, that's the idea is.
Okay.
Yeah.
Okay. Never heard about it, but
Reaching out to folks in NASA to see if there's a opportunity.
Okay.
Don't tell them how to trash it before you. Yeah. Leave that part out.
You know, the 3D CAD model was helpful enough for us. The 3D CAD model we utilized was helpful enough.
Okay.
Yeah. Also, we live in South Korea. Yeah, it's hard to.
Applause. So our next speaker is Brian here or Jordan? Is he gonna be Jordan? Okay. Jordan Kam from NASA Ames. He's gonna be presenting a rigid soft undirected tendon-driven gripper prototype for the free flying manipulator. So also here. Is he here?
Yeah, so right here. Yeah, that one.
There you go.
Hey, good afternoon, everybody. Sorry, I'm not Brian Colton. My name is Jordan Kam. I am a undergraduate rising senior at the University of California, Berkeley, up in the Bay Area. I'm also a research intern at NASA Ames Research Center. So today I'll be talking a little bit about our preliminary work that we did on a gripper prototype for a rigid soft gripper prototype for free flying manipulation in space. Oh, yeah, so and this is in collaboration with, as mentioned, Brian Colton, as well as my other mentor, Andres Mora, and some PhD student at Yale, Stephanie Woodman. So no need to harp on this. A lot of the talks today have already talked about some of the gaps that free flyer technologies and free flying robots can actually bridge on the International Space Station and in on-orbit habitats today. So some of the main things we've already talked about are inspection and maintenance, as well as logistics management. So logistics management, as well as maintenance opportunities. So on-orbit habitats, whether it's the International Space Station or future gateway concepts, some of these things are things that free-flying robots like Astrobee can actually bridge and do today in place of crew. And so how do we take some of these opportunities and look at what are the current challenges in these for free-flying robots and see if we can do, contribute novel R&D to that. So some of the things in terms of free-flying manipulation that has already been done, there already has been things like soft manipulation that's already thing, and it has a lot of pros. Soft manipulation is very safe. So I'm thinking in terms of on-orbit use, so it's very crew safe. Unlike rigid alternatives, it provides like a nice way to not harm both the objects it's grasping as well as nearby, and it also offers a secure grasp on the object in question. But some of the cons for that is that it has a lower grasp force in context, as well as a lower precision to rigid options. And then on the opposite side, we have rigid grippers, which have a higher grasp compared to soft grippers, and an increased precision. But on the downside is that sometimes they have poor performance when grasping complex objects in particular. So think spherical objects or objects that are outside of the purview of which you designed it in the first place. So it kind of lacks that modularity. So when you design a gripper, a rigid gripper, usually it's for a specific task. But without a hybrid, that was kind of the main motivating driver to work is what about you buying some of the both together? So we're on orbit, like legit this. For design, and actually we got to fabricating this gripper. So this gripper itself is a 3-finger gripper with rigid claws, and it is able to basically leverage some of the things in soft robotics like pneumatic inflation and actuation to conform around an object within the claws pneumatically. So it's still tendon-driven. So it's a 3-finger tendon-driven, 1 degree of freedom gripper, and as I mentioned, it can soft pneumatically kind of conform around the object in the grasp. But right now, currently, it's an open loop system, so there's no feedback going to it.
Recording in progress.
Probably just dropped off because we don't have Wi-Fi. Sorry. Share.
Sorry about that. But yeah, so we actually were able to develop both the design of this gripper as well as fabricate it. So for the actual soft compliant portions of it, we use traditional soft robotics techniques. So we, hand created a mold specific to the parts within the joints of the gripper, casted the mold, used elastomers material, actually kind of casted it and made it to the shapes that we wanted to, and incorporate it into the rigid components in terms of the rigid claws. And so I'll go over like a high level of like what the mechanism concept of operation is supposed to be for this. So we'll start off with standard grippers. So the fingers, so if there's 3 fingers, we'll look at just a single finger, and the mechanism is the same for all 3. So we start off with the finger at rest. So there's no actuation of either the tendons or the actual pneumatic padding itself. So it's perfectly at rest. And then we start by actuating the tendons. We pull the tendons, and the actual finger goes up like this and rotates around the tension springs, which are inside this region. And then from there, well, it seems like the slides are a little bit off. And then we actually then actuate the soft padding itself. So the idea is when you have an object within the purview of where you want to grasp, on orbit in microgravity, like let's say a screwdriver, for example, you can then first actuate the gripper to a place where instead of actually conforming with the rigid claws, you get to a plate nearby, and then you can pneumatically inflate the soft padding. And then that way it would conform perfectly around, let's say, a spherical object or another complex object of your choice. And so this way, it doesn't really matter what object you're grasping. Let's say it's a screwdriver, or let's say something bizarre like a star shape. The soft padding will be able to conform around this object, which is different from traditional rigid grippers, like let's say Astrobee's perching arm gripper, which is specifically designed to grasp a handrail or kind of a linear object like that. And so, yeah, so after we did all of the design work as well as the fabrication work for this, we actually were able to get to some preliminary testing at NASA Ames. And so at NASA Ames, we have this facility called the Granite Lab, or the Astrobee Testing Facility, in which we can simulate on Earth in 1 degree of freedom what it would feel like to be in microgravity. So as you can see in this picture, we have these air carriages that our Astrobees can fly on in one singular plane or in 3 degrees of freedom. And we did some preliminary testing by equipping our prototype gripper to Astrobee's perching arm payload and see how it would grasp some of these objects during flight. So this is a picture from that, and we basically attached the gripper to it, inflated it around a screwdriver, so it's a 2mm screwdriver, and see, we just did a very common F-plan task on the Granite table. Unfortunately, we did not go beyond just this kind of testing, but this is just a picture of what it looked like when we were doing some of that testing. You might notice one of the common things from this workshop is that a lot of terrestrial applications or space applications could be applied to terrestrial applications. So in terms of what are the general applications for this, pretty much any object that is rigid, when you're grasping an object that's rigid but has, fragile structural things you're to consider. So think like, glassware or like, fruits, or for example, or industrial applications in which you have an assembly line where there's multiple different complex objects and you need one general purpose solution for manipulation. So our proposed gripper could potentially have applications in these areas. And for some of the future work, we wanted to go into incorporating feedback, but if you guys all are familiar with soft robotics, this is actually a current research question now, is how do you incorporate feedback and soft sensing in some of this robotics? So we hope to do more work of that, but that's still being led in the actual soft robotics community. We also hope to do a wider variety range of testings with complex objects. So we only did screwdrivers for this work, but we hope to just test proof of concept for other objects. And we want to do a comparative analysis versus something we really know well, which is the Astrobee perching arm and perching gripper. We know that very well, but even that gripper lacks feedback, and that is another gap that our gripper would have to meet in the middle. So yeah, thank you very much. Yeah, it's silicon 0030 it's elastomer. Yeah.
So when you actually the soft part of it, you say it's pneumatically controlled. Do you have like force control on that, or it's just on and off? Actuate.
Yeah, so we don't have any force control on it. We have it connected to like the pumping lines that you can see, and we have it like connected to like a syringe, which is very common for demonstrations in soft robotics. So technically you could probably have some control, but for this we did not have any like actual pneumatic control.
How does your gripping compare to like other gripping systems in terms of like power consumption and these kinds of systems? Are they more efficient or less efficient?
We didn't do a study of that, but I guess intuitively, because we're doing less actuation on the actual fingers itself, and it's all primarily in the actual pneumatic kind of mechanism, it would be less power in terms of like the torque needed than traditional rigid grippers. But there would still be a power cost to actually pneumatically inflating the gripper, which is actually higher in soft robotics than it is in rigid robotics. So intuitively, it would probably be baseline around the same. Yeah. Thank you.
Is it possible to use it here? Is there an issue with if I put it here?
I don't know if I can.
I think this will be able to.
Second slide.
Let me see. This is we're recording and
Oh.
some audio here. Let's try. I know that we've done of them as well. Let me see. Is it one of these yours? RA, right?
Yeah.
Okay, let's try here.
Not there.
Is it different slides?
Yeah, seems so.
Yeah.
So we can just refer to the video.
Okay. Yeah, that's fine.
Do you have Zoom?
I have Zoom, yeah.
Okay, I can send you the link.
I can put on my Zoom. And then I share my screen.
Yeah, I could use my Zoom.
I use my hotspot.
Oh, okay. I'll send you Zoom. What is your? Yeah.
MEALY. ELY.
Really at cpp.edu.
Mainly, when I said machine.
Well, I think it's fine if we can put it. We'll get a recording from you later.
Yeah, thank you. Oops.
I always have links. All right, so our next speaker is Mohamed El-Hadedy.
Yes.
This work on A1632 channel low power FPGA multi-vertical EC for space robotics.
Thank you. So yeah, today I would like to share with you the work I've been doing with my collaborators, Professor Andrea from Switzerland, and my lab reconfigured the Space Computing Lab at Calpoli Pomona. So, this is a flight controller that is actually generating multiple of the protocols for the electronic speed controller for the brushless motors. And we call it Ra, which is actually ancient Egyptian god of the sun and power ship and, control ship. Okay, so that's why we have a really fancy logo for it. Okay. And thanks for the AI it created for me after 17 hours of work because of the iteration. Anyway, so let's go back to the. I like results more than talking about the story. Then I give you results. So we're gonna see reviews for the master students. Landry Renard. He actually coming from Switzerland. He working in my lab. This is the first one. Okay, let's start. This is
It's been then like the ESC should be like.
so it's what he did. This is an FPGA. It's called Pink Z, which has SoC 62-bit architecture, Cortex R, and it has a fabric of FPGA from lookup table and flip flops and all this soft core elements. Then what we did, we worked together on it. We used partial reconfiguration for adding the IPs of the D shots with different baud rates, plus PPM and PWM, which is used for controlling majority of the brushless motor exist in the market at the moment, and it's controlled by the flight controllers like Pixar and other flight controllers. So as you can see, what he's doing, he's putting the IMU on the board, and he's just trying to mock that that one is like lifting right or whatever, and you can see the 4 motors are spinning fully powered and controlled. So to reach to this journey, we started by the 1 motor, right? And you can see that from the next video. So the next video is another 2 students I have in my lab. We put the propellers, we put even our own speed meters to see how many RPM we are generating from the FPGA board connected to the motors. Our idea, it was completely migrating the electronic speed controller in FPGA by creating a PMOD that it has analog transistors will be connected to the fabric of the FPGA, so they need the microcontroller inside the ECs. And they're going to be one of the IPs used. And then, there's another video you can see here. Langley succeed on using the ELRS receiver transmitter to even control through the FPGA PINC Z board. Then, another video here, you can see for Sunny and, Langley, when we are using our oscilloscope to see the signals and see the jitters, coming from the different of those ESC protocols. So, this is what we have. Let's talk about the story. So, what is the story? So the story is very simple, right? There is limitation in whatever exists, and how we're going to achieve our goal, right? So if you look here about the scaling demands, if you would like to build a huge, massive robot or whatever, you can say cargo that is going to be flying, right? You might need multiple motors. I have seen a lot of videos from China about flying taxi. How many motors it will be, and all these things, right? Maybe 36 ducted fan. We built some of those drones in our lab at Poly Pomona, and you can come and welcome and to play with them. In the top of this, we know all of the story about the quadcopter that have been sent to the space. If you remember, it's a CO2, and it's a light air, so that you have to be spinning really quite fast, or you have to change the whole entire structure to a bunch of all those motors that are going to be spinning like crazily, massively number. It will be stable in that same air, right? So if we give them this controller, that will be quite interesting. I know one guy will come and tell me, but is this FPGA is hardened, red hardened? We will talk about this later because we can put TMR there. Anyway, then in orbit service, within around 24 to 62 micro thruster for precision docking. Because my team is working in drone docking, a swarm of drone docking, detach and attach at the same time for replacing data in the memory to work as an HPC using orchestration Kubernetes. Then the limitation of the today ESCs, since we are talking about ESCs, right? So it's MCU based, it's a microcontroller based. You're talking about 4 to 8 channels, and then the jitter is around more than 1 microsecond. And the top of that high per channel power, you're talking about 2.5 watt, and the CPU is overhead because you have to talk into the CPU all the time, right? Then non-unified multi-protocols. One of the story I need to share with you, because of the Ukraine-Russian conflict, there was a company located in Norway who were creating the software for the ECs called BLE32. And this company, because of the geopolitical situations, they shut down. Then all of these people, the hobbyists or whatever, they were suffering until they said, what, let's make something that's called AM32, which is the standard for the ESC software. But to flip all of the exist drone to AM32 is painful, But with our situations, we don't need to flip to anything, because it's completely intellectual property on the fabric of the FPGA, and it will be detected self without echo. Our goal is to determine defining less than 50 nanosecond jitter entirely in FPGA fabric, and we are working now also on putting in Jetson as a one processing element instead of even using FPGA, and the rest of the processing element will be for some natural language processing because we are controlling drones using NLP. Then scalability, instead of using 4 to 8 or 12 channels, which is going to be 12 motors, we're talking about 16 to 32 channels, and I can tell you we can even control up to 1,024 motors at the same time. But our limitation in this board, it was the I. That's the whole thing, which is the pin of the PMOD. Energy efficiency is less than 1 watt per channel at the hovering, when it hover really quite high to the limitation of the FAA policy. Now we're gonna move into the limitation of the ESCs. We already covered it, but I just wanted to represent it in a different way as we learn as in engineering all the way leads to Rome, but you already have a bunch of routing, so maybe this slide wasn't clear, so this slide will be more clear. Now, because of the time and I speak faster, so let's go directly to the architecture. So the architecture of RA, as you can see, there is a 4 motors that we already connected to the ESCs, and those, the ring Z2 is controlling the IMU, the GPS compass, and it's taking all of this interesting information through the partial reconfiguration surrounded by 2 different experiments. One was microblaze as a soft core processor, and the other one it was with ARM Cortex A9, which is already laying on the board. Why? Somebody will tell me why you spend your time in a soft core processor? Because end of the day, it has its own job. I can replicate it many times, and then I can make multiple TMRs inside, and then if something got broken, the rest it will be doing the job. But then the limitation, it was coming from the microblaze, because it was just controlling up to 16 motor because of the cache inside that microcontroller is very small, but you can actually extend it if you have a DRAM and other sophisticated boards. And then if you look here, processing systems, as I mentioned, it was microblaze soft-core processors, ARM Cortex A9, which is a quad-core, and then we already have the AXI timer, so we built an AXI timer that it will be calculating because we don't have an operating system in that case. Then peripherals that was there, ESC array of 32 channels of brushless motors, sensors like IMU and GPS, telemetry, even it was using the ELRS, as I mentioned before, and radio RX that it was actually sending back and forth using UART. Now, it's painful to look at this table, but I will give you the summary quick. Here are the most famous protocols using for controlling ESCs. PWM, pulse width modulation, PPM, position, pulse position modulation, and then D-Shot, which is the high sophisticated one, which is digital. The rest of those guys I mentioned are analog. So those are different baud rates that the D-Shot can produce, and you can see here the comparison between of them in signal type, a channel per wire, resolution steps, nominal update of the rate, line speed, and of course error checkers and the throttle calibration and telemetry, as you can see. So what is the most interesting thing to come out of this table instead of bothering your eyes looking here and there? So most important thing is digital. But digital, that means you're going to be using CPU. But if using CPU, that means I'm lying, because it's overhead. But it's not using CPU, because we are using what? Partial reconfiguration, and the IP is isolated by itself, doing its own deterministic job, while the core is doing the PID and EKF, enhancing Kalman filters, and all of this sophisticated things. Then, we're talking here about, the resolution. You're talking about the resolution, since it's digital, it's around 2048, 0 to 2047 resolution from the 11 bits. One also thing, we mentioned here the telemetry. Look, we said optional bidirectional heli, which is basically the one, got broken, and now, the already AM32, but, we are making our own, which is going to be open like one nest making their own SHA-2 reflection. Anyway, so if you are really interested to know how it works in this IPs, here is a really interesting tree that we created for every single element while it was in the IP. So, if you look carefully into the D-Shots, the D-Shots is basically the golden excellence. You can figure out that we have encoder, that encoder looking into the rate of the kbytes per second, which is basically 1500, 300, 600, 600, 1200 kps, which is little finite state machine doing that without interacting with the CPU. Also, we built some error detection in the finite state machine to catch any error without affecting in the total latency, so the model will not be interrupted while we are flying in the air. Now, if we go into the rest, this is the state of the art. So PPM and PWM, we know, right? Clock is kind of PWM, unless the duty cycle is going to be the turn on based on the sensor that we already have, and the rest will be the turn on. So, we don't need to waste your time on that. PPM is already analog, and most likely of all of the new motors and brushless motors really trying to avoid PPM. But we respect all of the old technology and new technology, and we know that and people work in FPGA, for instance, in the space. Vertex 5 for 17 million years, it was the one officially used in all of their missions, right? Until they red hardened the Kintex Ultra Scale, and now they already red hardened the Versa, right? But if we would like to use whatever we have, right? This block it's already covering everything, PPM, PWM, and D shots. You just log your motors, automatically it will figure it out and just run it within less than 15 nanoseconds. And then we already have also the GPI, the UART, which is basically the lovely thing that we use for the flight controller in general. Now we made a very good, interesting graph, as you can see, up to 16 motors. Based on this equation about total power, when you are going in the maximum thrust, you will find out the actual and the real and the simulation, they are really close to each other. But after 16s, it starts actually going in one linear. Because our simulation was this line, but the reality, which is collecting the data, is deviating a little bit, which is around 15% in the max when we go in the 32 motor. The reason for that, the wiring. We know that all of this type of ping Z and stuff like that is really trashy, cheap material for making the GPIO. But when you go in a sophisticated space application, most likely you're gonna be using gold, diamonds, whatever material that are gonna be really quite interesting. Then the curve will be what identical. Then let's go into the price. So the price here, the FPGA is expensive, but per channel, you're talking about $3.13. I like the 17 cents because I calculated 17,000 times. The file controller of the ESC, this is the one we use, which is a 50 amp maximum in the continuous, is around $12. The motor we're using, the maximum thrust coming from the KV750 is a $15 each one. And then the propeller, the max propeller that they're gonna give us the maximum thrust is around $3. The wiring and connection that I already bought it for this experiment was around $5. And then the total of this game, it was $38.18. Okay, so if you look into the comparison here, you will find out raw system delivers around 2 times more channels at the third cost of the whatever exists at the moment. Then if we look here about the worst case control signal jitter comparison, compared to the other people, the state of the art of the people worked before, you will find out, STM is the most sophisticated, microcontroller used in a flight controller, right? And if you look into here, those two gentlemen, they work together and they reach out to 1.2 microsecond jitter, and the reason we are using PPM and PWM. And PixHawk, which is everybody's using at the moment, is 1 microsecond. Lee and Kim, they try to play with microcontroller FPGA together, and they achieve 0.5 microsecond for jitter. But Wang and Shan, they tried to play with the D-shot by itself with FPGA, and they arrived into like 100 nanosecond. Beton and Seng, they did almost the same, but it was for PWM, and they got around 100 nanosecond period. Raw, less than 50 nanosecond, deterministic, calculated, and even look into the oscilloscope as I showed you in the beginning of the presentation. Now, space readiness, we built a huge Tesla coil in the room, and we made the drone to go around them. And to see the effect of the EMF will come from the Tesla coil on the whole entire setup. And we found out some stuff, which is pretty much everybody know the result. The compass will be affected because of the magnetism. But if we can have more EMF, that would be more fun to see what will happen. But we know the result because also this board is not really red hardened, it's not really space graded, but we play with it because it can be used also for industrial drones application. Then let's jump to the conclusion and impact. Raw highlight less than 50 nanosecond jitter, 16 to 32 channels for this board. CPU and zero CPU, because we're not using CPU, around 1.9 watt per channels, $38 per channels. Performance, our performance of the microcontroller hybrid system between microcontroller and FPGA, we are getting better and better and better. Futuristic stuff, we're going to be using red hardened FPGA, TVAC, and that would be more fun, to try to burn something. I like to burning stuff. And then, also we try to implement a module of IP inside the flight controller that's going to be NLP, because, we have a grant from the US Navy. We control the drone using natural language. And we're word, which is a model of the audio to the text that is actually, you can yell to the drone and say, don't shoot the other, then it will not shoot him. Anyway, so I would like to thank all of my collaborators and actually put their money and effort to help us. So, AFRL, NAFC, NASA, is my lab and made a very nice logo for it. And then, that's actually my lab also, which is another logo, all of this fancy Egyptian gods, ONR, the Navy, UIUC University of Illinois Urban Champion because my supervisor actually he moved to be an NVIDIA guy at the moment, when Mayhu. And then US Force Academy because I've been fellow with them for almost 5 or 6 years every summer. Thank you for all listening to all different languages and any questions. Yeah.
We heard so much great thing about everything that you did. Can you talk about, let's talk about what do you think are the limitations apart from the space training?
Limitation. I used to be a senior design engineer in a company called Atmed, which is a microchip, right? Verification. We need to be making a lot of verification, and especially with UVM, that would be more fun. And the other thing that I haven't tested fully all of the AKF, the enhanced Kalman filter, especially when wind hard it will come. I built a little rocket to shoot the drones to see if the drone it will be standing or not, but it's safe. Hopefully I will hit it more to 60 degree and it still will be safe. I didn't try the part yet. So those are the things that I would like to see.
Thank you, Mohamed, so much. Nice presentation.
You guys already know me. My name is Jordan Cam, as well as Brian Colton in the room. But this work really stems out of a passion that me and Brian have in strategic road mapping for future robotic capabilities, and really what NASA should do and other space agencies should do to invest in the future of robotic capabilities. And I don't need to talk more. I'll just have a quick overview slide. You guys are all experts in space robotics, so I just wanted to highlight some of the the types of space robotics that we're not covering in this. So everybody knows the planetary rovers. I actually learned a lot more about reconfigurable robots, and you have arms and manipulators and even humanoids, which are from talks from yesterday's things. But we're not covering any of this in our review today. Instead, we're looking at free-flying robots, which is actually something that's come up a lot in this workshop. But particularly, our review wants to do a deep dive into free-flying robots, but the intra-vehicular free-flying robots. So free-flying robots that flew inside a habitat or inside station, rather than EV robots or extravehicular. So there was actually a talk yesterday about Seeker. So we're not looking at things that flew outside or in shuttle. We're looking at things like that flew inside. So this slide kind of just shows a nice distinction. This slide kind of just shows a nice distinction between the two types of free-flying. In my talk, we'll go over specifically each one of these aspects, and I know a lot of you guys probably know a lot about these free-flying robots, but this review paper was mainly just to do an overview of the concept of operations, the capabilities are in development, kind of initially what they were intended to do, and see what those concepts of operations look like, what their contribution is to the state-of-the-art of free-flying robots for IV free-flying robots, and just kind of outline what this and how it could roadmap to lessons learned to see what are the gaps that need to be developed for future free-flying robots. So the first one we'll talk about is Sphere. So this was the first ever free-flying robot, IV free-flying robot that was flown to station, and our review covers only the ones that have actually flown to station. So there have been a lot of concept of robots that have been developed by different agencies, but we're looking at the ones that actually flew to station. So the first one was developed out of MIT. So Spheres, or the Synchronized Position, Hold, Engage, Reorientation Experimental Satellites. It's a long one. I know, Andres, you've worked on Spheres, and a lot of other people at NASA and MIT have worked on this. This was the first ever free-flying robot ever flown to space. So it was developed by MIT. It was funded by DARPA, NASA, Aurora Flight Sciences. It was flown in 2006. And this was really the first of its kind to test satellite formations, constellation kind of guidance, navigation, and control algorithms. And it really started the model of free flyers as a test bed, Free flyers as a test bed, right? For future
free flyers
to come after.
And so originally it was kind of like low-cost, long-term ISS test bed to test GNC algorithms. And it also had a lot of other fun stuff like its own guest science program that it had, as well as a K-12 outreach program through MIT's Zero Robotics competition. The next one was developed by JAXA. So INBAL and INBAL 2. So they were developed at different times, but we wanted to group all the series in the same family together. So if you attended Jungil's talk, he kind of already went over some of this stuff, but INBAL is the internal ball camera, so it's developed by JAXA, and the second one is the same thing, but with the two. It was developed and funded by JAXA in collaboration with local universities in Japan and some AI institutes, and it was flown in 2017.
So it was a couple of years after Spheres, so there was a kind of a large gap between when Spheres were flown and when In-Ball was flown, but In-Ball was the next free flyer after Spheres. And then In-Ball 2 flew a couple years after that in 2023. So from one series to another, there was increased autonomy for navigation and increased perception. In-Ball was primarily a perception free flying robot. It had a large camera module, it had a complementary metal oxide semiconductor, digital camera module on board, and it had a lot of high performance embedded CPU. It had a high performance embedded CPU on board. It was primarily for perception. So originally it was developed to reduce crew time in routine maintenance tasks. So it was in the GEM to basically do very routine maintenance tasks. And there was even a study where it said it was able to reduce some of these tasks by 8%. And that paper was presented by Jackson. The next one was Simon. So a lot of people actually don't know about this one, but it was developed by Airbus and the DLR. It was a one of its first of its kind to develop kind of the intersection between like AI and free flying robots as well as human robot interaction. Extremely cool free flyer. It was flown in 2018, shortly after In-Ball in 2017. And then there was another one, Simon 2, that flew just the year after that. And Simon 2 had increased autonomous navigation and increased battery life, very similar to like the In-Ball and In-Ball 2. And it actually had voice-enabled free flying, voice-enabled free flyer with AI capabilities. It had facial recognition and it had NLP as well. For that kind of like conversation. So it was meant for, developed for like conversational interaction with crew. And yeah. The next one that came after that was our favorite Astrobi. It succeeded Sphere, so it was developed by NASA completely, and it was the one that came after Sphere, although it came many years or decades after. And it was funded by NASA, and it was flown in 2019. And Astrobi was a contribution to state-of-the-art where it really allowed hardware interface, so whereas none of the free flyers, or very few of the free flyers had this kind of hardware integration capability, Astrobi brought that in terms of payload integration and payload testing that it could do. So it originally was designed to do assistant crew, which a lot of them are, and it was meant to kind of reduce crew times through things like manipulation, perception, and guess science, which are some of the things you've already heard in a lot of the talks. And yeah, it also continues Sphere's legacy of the Guest Science program, and some of these other projects that I have put in the parentheses are talks either given today or from colleagues that we also. And it also continues Sphere's tradition in the zero robotics competition. And the last one is this one that just launched a station in January. Not much is known by it. It was developed by the Chinese Space Agency. Yeah, so this one was developed by them. There's not much information known about it yet. We just wanted to include it because this would be an appropriate place to at least include that it's happening. Not much is known, but there's a fun video of them teleoperating it, flying it around the station. And one of the key things that we wanted to do with this review paper is just kind of see, you're given lessons learned and given this kind of thing and see what are the opportunities, gaps that are done, and how can we use them for future road mapping and developing future free flyers. Thank you.